I have shared my screen. Okay. So today I will be discussing four of the problems which I had given. One is the code forces one. The second is INOI 2022. Third one is event hopping, and the fourth one is APIO jump. So that code forces one had a proper editorial. So I will be explaining that at last if I get time. And if someone has doubt, then let me know. I'll solve it right now. Else I will explain that in the last. So yeah, let's start with this problem. I know 2022, which is Conquest. So I hope you have tried the problem. So in the problem there are like n cities and n minus one edges, bidirectional edges, and there are q queries, and in each query it travels from AI to BI, and so basically it is a tree, and in each query you are given two nodes A and B, where you have to consider the path between A to B, and the thing you need to do is each node is assigned a value. Okay, so it's like a tree. Each node is assigned a value. Okay, so each node has a value, and what you need is basically for some node, let me say from S to T or A to B, you consider the path between it, and in this path every node has some value, and you need to take some of the nodes, take the values of some of the nodes and add it such that the sum is maximum, and the condition is you cannot take two adjacent nodes. That's the condition. So since you want to avoid causing too much discontentment, he will not loot two adjacent cities during the same expedition. Okay, so you cannot take two adjacent nodes and add their values. So this is the condition. So of course, for finding the path, the first thing that will come in your mind is you have A and you have B. You will just find the LCA, this node, and then you know the path between A to LCA and B to LCA, right? And now you need to find the answer. Okay, so it's like two parts. First, it's like the first part and the second part where LCA is again, like you need to have a condition of LCA choosing in only one of the parts, and you can solve it, right? It's just a line graph. You just go up and up and you just solve it. But the thing is, you need to merge answer of this and answer of this, right? And you also don't know how much above you need to go. So again, to find this, as usual, we will think of solving it in parts, and then we'll try to merge it. So if we can solve in parts and we can merge it, then we can solve for a line graph and merge those. Here also we can solve for a line graph and merge those, and these two line graphs can be again merged because they are again adjacent from this edge, right? So we'll try of solving this problem with paths and then merging those paths. Okay. So what is the answer for only one node? Only one node is there. Then answer is either zero if you don't take the node, or a of node. So let me say a of u. Okay, this is u. So these both are the answers if you don't take and if you take. Right now, suppose you have a range, like these are the nodes adjacent to each other, and you have another range. These are again nodes adjacent to each other. Okay, and so you know everything you need to merge these both range to make it a single range. Okay, so you know everything that you need to merge. Suppose you know the max value in this range, the max answer that you can get. So it might be taking this and this, or it might be taking this and this, whatever is it. Okay, and same goes for here, right? So the things you will be knowing is sum or max, sum. So let me assume it as sum max is one parameter you should know. The second thing is when you want to merge, you know that here the condition is satisfied in sum max, here the condition is satisfied in sum max. But the thing is, when you are merging, you can't take this node and this node, two nodes which are adjacent to each other, because these are also going to have an edge between them. Basically, you are adding an edge, right? So you just need to have a condition where you check that this node should not be taken and this node should be taken, or basically both nodes should not be taken. So let me say that it has, let me say this is start, different color, let me say start, end, start, end. Okay, so basically you need the end of the first range and the start of the next range to merge those. Okay, you can also say left right, whichever is fine. Okay, so now what the condition is, if I don't take, let me say 0 represents not taken and 1 represents taken. Okay, so what are the conditions I can have? I can have 0 at the end and 0 at the start, like both are not taken. Or I can have 0 at the end of the first and 1 at the start of the second. Or I can have 1 at the end of the first and 0, where is my cursor? And 0 over here, or but you can 1 is not possible. Okay, so these are the three conditions that you can have. If you have 1 then you are taking both adjacent, right? So let me find an answer with end of this is 0. Let me have, and when end of that range is 0, let me have the sum max value, and start is 0, let me have the sum max of the other range, and the complete range will be whatever the start value is it has, whatever the end value it has, and the sum max of 0 at the end of the first range and sum max of with 0 at the start of the next range. Similarly 0 and 1, 0 and 1 and 0. These are the three conditions we can have, and for each of them we need to have the sum max, right? And now we can see that when this range end, like when we after we merge the range, okay, we have a new range, and when we this new range merges with someone, it has the end point as start is nothing but start of the first range and end is nothing but end of the second range, right? So again for those 0, 0, 0, 1, 1, 0 and 1, right? Because end can have any value and start can have any value. Start can have 0 and 1 and end can also have 0 and 1. So 1, 2, 3, 4 values are possible, right? Here the start and end can have same one, because they are like starting and ending and not adjacent to each other. When the length is 2, we will need to have a case, like we will need to make it manual to make it like at most one of them is 1. But if it's a long range, after that we can just do recursivity and we can just find like for each of the 4 conditions, and there will be again 4 conditions of the left side, like another range with having start and end, and then again you can merge using discarding these two and using these two finding the possible cases, and again keeping this as the start of the new range and this as the end of the new range, right? So this is again what, so basically you are again merging things in order of 1, right? And how many merges you can have, so it's like a similar thing like a binary lifting. Basically first you have 1, or let's suppose 2, then 2 is merged with 2, this 4 is merged with this 4, this 8 is merged with this 8, and similar in binary lifting, the similar manner we can also lift by use binary lifting to find this values, right? So as we go on with binary lifting, we will also calculate these values, and since the values of the array are static. If they are not static, then we need HLD, which is like a very more advanced topic than this, more harder than this, and more tedious to implement. This is also not easy to implement, but that's more tedious. So that's what we can do is we can just calculate as we go up with a lot of caseworks, and similarly we can have LC in one of the parts and another part, and again while merging these two parts, while merging this part and this part, okay, here the thing is this is start, this is end, this is start, this is end, because we have a line graph, right? So here we are merging end to end. This you need to keep in mind, and especially you need to have a function which merges end to end, and you need to put these values, right? Yeah, that was all the approach of this problem. Yeah, it looks a little easy approach, but the implementation is really not that easy. My implementation was very bad because this was like a 2 years ago, but still I will try to explain it. In the approach, does anyone has any doubt, or should I go to the implementation? Okay, I'm assuming no one has any doubt. Yeah, so let's go on. Basically, this is again start, 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 end. Okay. This DP is nothing but for all nodes, all binary lists, two start positions and two end positions is the DP. So we start by taking the input of each array. We have adjacency list and we do binary lifting. Okay. So binary lifting includes all the pre-calculations. Okay, it is a very messy code and with a lot of casework, but I'll like try to make it as easier as possible. So it's nothing but parent you get. So basically for the first only node, single node, you know that you can only have 1 1 or 0 0. So I've just taken 1 1 because for two nodes also we need to do it manually. As I explained that for two nodes also there is a case where start and end do both can't be one, right? So that's the thing. So for both of those, one answer is zero, and it's like globally initialized. So we have initialized it with zero. So I have commented this line. So basically, assume that all DP are currently zero. So DP of 1 comma 1 is array of node because when both start and end is the same node, it's 1 comma 1. And for size 2 also we do it manually, and it's for size 2. Let me for 1 comma 1, it's either the left node or the right node. We can't take both nodes, right? So this is the start node and this is the end node. 0 1 comma 1 is nothing but 0 1 comma 1, which we like initialize with the same node. So I'm just finding the value of that. And 0 comma 1 is nothing but taking only the node above it, and 1 comma 0 is taking only the current node, and 0 comma 0 is 0 because we don't take both nodes. Okay, and we do up for this also, and then for we do binary lifting, we get the parent, and these are the starting nodes and these are the ending nodes, right? So load I start t and t1 is basically now I have merge function. Okay, so how am I merging the two things? So what I give is I have a node and I have up of node of I minus 1. Basically, this is the start of the next range and this is the start of the current range. Okay, I is the size 2 to the power I minus 1 is the size of the range of both the things, and T and T1 is basically this transition. So I know that this range should have T. So if T is 0, then it should have starting as 0 and the other range should have ending as T1, right? Because we have T1 as this. Okay. So this gives the start of the resultant and end of the resultant. And how do we merge? Yeah, how do we merge these two ranges? So I comma power is nothing but I with it to the power I minus one whatever, and type and one. Okay, so the thing is I power type and one. So basically, you are at the I node and you need I minus one. The power basically to the power is the length, and type is nothing but the type you need, right? At the start, because and this is the type of the second row end. Okay, this is a type of the start, and you take one app behind, then you can only take and the second means zero in the like start, right? You cannot take one and type one because type one is the end. Or I take type and I take zero over here, and I take one and type, or I take type zero and zero and type. All three options. I can't take one and one. Okay, this is a merge function. There is a final lifting. Yeah, so we just merge and we just continue binary lift. So we have initialized it. This is just finding if it's an LCA or not. And this LCA gives basically LCA A, and these returns two things. Basically, this is the LCA and this is the LCA minus 1. Okay, so why we, because we can't take LCA in two times. We need to only take LCA once. Okay, so now let's go on the code. We set dp by 0 manual lifting, and therefore each query a b, these are the nodes, and we get a pair, and if the second pair is minus 1, that means a or b is one of the LCA. Then if it's b, then find a to LCA dot vf, else find b to LCA dot vf, and basically max of this. So basically it's a line, so I can only find a to basically A to B or B to A, whatever. It's just a line. Okay, we don't need to merge it again. So it's like max of x1, x2, x. Basically, this is both zero, only one, 1 0 1 1, and 1 0 0 1 and 1 1. Basically, binary bits. I can just convert it instead of two transitions, only one transition. And else we have basically this find function gives the max possible value you can have in a range, combining the different possibilities. Else we have x and y, which is first is lca dot vf and second is vs, and then second is lca dot vf. Okay, so basically x to a and y to lca, these are the two things we get. And after that we merge x and y, but this is a different merge which we use, it is, which we don't use in find, and then it's again max of all four things. Okay, so now let's go on to find. So we just go, if it's not LCA, then if z is in, just as the size is 0, then we know that this is our first range. So just push back 0 0 0 1 1 0 and 1 1. Okay, else we know that this is a new vector and we need to merge z with this second range. Okay, so z becomes a complete range and we go up. How do you, what is our merge one? So as I explained to you, the merge one is a1 plus b0, a2 a0 plus b2, a0 plus b0. So basically it's the same thing, 0 plus 0, 1 plus 0, or 0 plus 1, it's the same thing. For 1 it's like second one is 0, so accordingly I do the transitions. For 2 is like sec 2 is again the, like one of them is 0, so I need to compulsory keep one of them as 0, and the center one can change, so accordingly I do. And when both are 1, so it's like 3 is like both 1, and 1 is like only inside one of the inside elements can be 1. So that's the three condition. One inside, like the end of the first term is 1, start of the second term is 1, or both, and then start of the both the terms are 0. So I'm talking about the center one, not the edges one. Okay. So as I explained, this is how we merge. And if x is equals to y, that means we have not taken this only element. Okay. So in that case, we have, if we have z dot size equals to 0, z dot size should always be 0, I suppose, because if it's not the case, then we never touch x y. So that's the case. Else vector LL temp, so else we have temp and we merge, but it should generally go over here. And if we like don't come, that should also not be the case. Then we just assign by initial as 0. And if x not equal, so here we are only taking I as 0. Here it is I as 1, because x is not equal to y, so we need to take x and we need to take y, because x is like we increase x such that we don't take LCA, and the x is also not taken. Remember that LCA is like taking the, you are on an element which is not taken, right? So x is also here, x LCA, which is x and y itself, is not taken. So we only take LCA here. Both LCA and x is not taken. So I merge with I is 1 over here, because the size of the range is 2. Right, and it's the same thing that I'm doing everywhere. If size z dot size is 0, then include every make a new z. Else it's like keeping it, merging it. That was, and then merge 2xy is nothing but, basically this is special function when you have end to end merging and start to start are at the end. So it's the same case work, and after you merge, print max of this. It works correctly. So I hope you got it. If you have any doubts, then let me know. Okay. I'm assuming there are no doubts. Okay, so let's go on to the next problem. Event hopping. So here you are basically given ranges. Okay, and basically you can have SI, EI, EJ from a event J. You can go to event I only if EJ is in middle of this. Okay, so basically let me make it as a graph where each position has an edge. Only if, like, there's an edge from I to J and J to I, let's keep it separate for now. Only if J, end of J is in range of start to end of I. Same here, end of J is in range of start to end of I. Okay, now we need to find the minimum path. Okay, so suppose we have in some range and we have another range. So let's suppose we have now q queries, and each query you are given start and end indices, and you need to find the minimum jump. So let's suppose start has some range and end also has some range, and it's possible to visit. Then there should be some j over here, and it's some range, then there will be some range over here, and if we keep going like this, you can see that it will always be a continuous path and no position can be left, because j is like in max it should be connecting, right? So it should be a continuous path, it cannot leave some index I, right? So from this observation, we can find that for E, for this I, S of I, E of I, the best position that I should jump, instead of having like many edges, I can only have a best edge. And what is that best edge? That best edge will be some E of J which has minimum S of J. Okay, in this range, from all E of j, we want minimum S of j. Why so? That is because if you have some S of j, which is if you have some here is the S of j and here is S of k, right? So for all, pardon, yeah, I got, but for this, how you will use the exchange argument? Okay, okay. So like so suppose S of k works. Okay, S of k is better than S of g, but it's like, but then you have all the values. Let me say here, right? So for all values, so let me say it has a longer range. So there are some values of here which are like not included in S of J, right? And there are some values here which are not included in S of K. But S of K is better. So S of K has can reach to more lower values or more wider range of values. But no, that's wrong actually. S of J is better, but if S of K would be better, but it's not possible because for all values over here we can have a direct reach, right? So it's like a distance of one. We won't go to S of K, and for all values of here, we it's the same that includes S of J as well. But these values S of K doesn't include. So these are values are specific to S of only J. S of K is not including. Oh. It is like a old problem or a new problem? Okay, I'll continue. So basically here, you know that there are like more better options you can visit, right? So it is always best to go to a minimum S of starting J in the range, right? So instead of having multiple edges, we'll just have a edge with the best minimum possible J you can go. And when you know, so let's start from a start to end, and we are for now we are going backwards, right? So for this end range, we'll have some range, end range will have some range, and we know that this is a continuous range. And if any time, let's say E of S, okay, so ending of the start E of S. So if we have any time we have a range which is like coming like extending till E of S or more, then we know that we can also visit S because S has some range and our current range is some range like less than S, right? So it's like some include, it's gonna include S for sure because its start end point is of course more than E of S or greater than equal to E of S, and its start point is like less than E of S. Because if we anytime like we visit, even if we visit S itself, then its endpoint will be like equal to E of S and start point will be equal to S of S. So we know that our start point is going beyond E of S, so we like stop here, we can't go, we don't need to go ahead, right? Because we have continuous ranges. When we extend this part, we know that we can have a jump here as well because its end is in the range, right? So now we see that there are some number of jumps, and this has a graph where each node has at most one parent. Some nodes might not have some any parents, and this is not like this is a forest. There's some graphs, but you know that each graph is a tree because the root will have no parent and all the other people will have, all the other nodes will have at most one parent because we take the maximum left possible, right? And here we can binary lift on all the nodes and we just find when it exceeds S. When it exceeds S of E, and once we find that, we just need to find the number of jumps we had, and that would suffice. That should suffice. Okay, so let's go to the code. Does anyone have any doubt in the subtask, which I haven't really solved in subtask? But if anyone has any doubt. Training in cities, high station is possible to party only in station one. Minimum to the school one. Yeah, this is also similar, but here there is a price, and in our case, price is always one, right? Because there's just one. So let's go to the code. So actually, we don't need a pair, we just need a minimum element. But I had a wrong approach of finding the minimum index instead of the minimum value, which gave me only 30 points. But then I found the bug. So we just need a range min segment tree to find it. But yeah, let's start. So basically, you have, yeah, sparse table is also fine. You just need range min, whichever data structure you want. So range min you can be solved with many data structures. Range min, range max. So first the thing is, yeah, I forgot the thing to say is now when you have edges, you need to sort the array by E and not by indexes because it's like a random. But we are like going on continuous ranges, right? So the first thing we do is sort the array and we are going backwards. So we are sorting it by E values. Okay, so we put the first element as the ending and starting and position sorted. This position shows that where is the that position in the E sort position. By sorting E, where is that position? Which is at I, right? And reverse is when you have that E sort position, then which position, which node is it? That will be at the I position. It is E sort I dot BS. Okay, so it's just the reverse of position. So we can get both things. Set tree is for arrangement for having the first edge. After that, we can have like a binary lifting. So this is just initialization, and here comes binary lifting. So the first parent for each will be, this is a start of the current element, and we find lower bound. So we find the left part of all the nodes. So if left is the node itself, then you know that there is no parent, and parent is the node itself. It's a root node. Else we know that it's in the range of I excluding I to the left. So there are some nodes in those start of current node and end of current node. And we check all the nodes and find the minimum starting point those nodes have, and we will go to only that node. So a parent will be that position only, right? And then we do a normal binary lifting and answer on queries is if both are same, then we like both positions are same, then we need zero jump. This OGS is nothing but the position in the E sort array, and OG is ending position of the in the E sort array. And we know that starting is greater than ending position in E sort. Then we it's a graph like you have an array, this is ending and it's starting. This is the situation possible. It's not always that. Here also there is a case where like it's an completely including array or something. Yeah, it's a completely including array. So in that case, we need to print one because you can directly reach in a single step. But if it's not completely including, so basically either if it's this case or it's this case, right? This is E and this is S because S has greater position. So if it's this, then it's like one chance. This is like not possible. So should be no. Actually, this is also not possible. What have I written? So okay, start. Okay, it's like start has endings. Okay, if it is for having same this node. Suppose we have something like this, right? So for that, which one is ahead, you don't know. So for that, we can reach in one position. It's for the same node, and else it's not possible. So that's what I'm checking, that start has an ending position in the range of the ending. So here is the start ending position, and it's of course greater. So it would always be here. It cannot be here, right? It cannot be here as well, as it's not possible. So that's a one direct answer or impossible. Now I know that it's like a normal range where start is here, end is here, right? So we will have minimum is the start, which like we will where we will end. We are like going backwards, and it's the ending of the start. So we don't we once we exceed this, we need to stop. And if it's not exceeding, then we take the answer these many nodes and go up. And if like still we in the current node when we reverse, so basically this is like according to the e sort, so we need to use a reverse every time, and after we reverse it to the original position, we can use vector v to find the values first and second. And if it's still greater than mn, then I need to go like this is the lca part normally, and now it should be less than equal to mn, right? So here I go. uh, Yeah, and we have one more answer because now we only reach like this is like number of edges, and we need one more edges to go on that node, right? So it's like this is only one, this is two. So suppose it's like E and it's like S. So I know that the minimum of this E is already in front of this S. But now we need to go from this E to this S, which takes one chance. Like so, similarly, when we know here, we have came to a node which has like a minimum value greater than less than mn, less than equal to mn. But now from that node, we need to go to this particular node, which takes another chance. This is a corner case. Like I also came, what I had to go through, and now it's still greater than mn, then I know that it's not reachable, so it's impossible, else I print the number of jumps or edges I used. Yeah, that's the whole thing. Does anyone have any doubt? I mean, ask you. Okay, start to end. Actually, we need the end values, so I felt it easy to go from end to start. But start to end, you need to like maximize the end every time, and you need the end values. It's better to go from end to start to end. It's, I'm not very sure about that if it should work. But yeah, 30 points you should get. Now the next problem, if anyone has doubts, then let me know. Let's get started with the next last problem. Rainforest jumps. This is a pretty tough problem to think about, and implementation is also on it. Like I did a very bad implementation. So basically, you have like heights, from, okay, let's start. So basically you have some array, and this, from this you can go to left. First element on the left such that it has height greater than this height, and first element on the right is the height has height greater than this height, right? So basically for each node can add at most two edges, right? But now these two edges, right? And the thing is, for each query we are given like two ranges. These can be like interchangeable, and we need to go from here to here in some range, or here to here in some range with minimum steps, right? So I was solving some tasks, oh, like not this time, but I think I had reached till here or something. This, it was tough for me, but I hadn't implemented it. When I implemented, I thought for full, but you can, because it's not easy. For the first time I tried, I was also unable to solve it. The second time I tried for the lecture, I was able to solve it. I don't know why. Yeah, that's a good thing. So I'll go for the full solution. You can't think of the subtask because it's a quite hard problem. So the thing is to observe a lot. The first thing is, let's have a graph where this node only has a graph to its left, where a node has only edges, like edges to its left, edges to its right, and the third thing is for this node edges to the maximum height that it can reach on the left or on the right. Okay, and you know heights are distinct. It will be exactly one edge, right? So each becomes a tree because each node will have at most one edge, and the maximum node will have no edges, right? So we have three trees. One is left tree, one is right tree, and one is max tree, right? So these are the three trees we can have. Now the thing is, here there will be always be two cases. One is A B C D and one is C D A B. Okay, so I will only be explaining for A B C D, and you can always think about, like, it's just changing the variable and doing the reverse in C D A B. That's it. It's nothing that, like, somewhere the signs might get changed, and that's all. So that if you understand the problem, then I think you should be good enough to change this transition. So I'll be focusing on only AB to CD, right? It's like doubling the code, that's all, or using a good way to code, unlike me coding like copy pasting every function and then changing the minor thing. You can have a proper method to do that. But yeah, let's see that we have, like, for conventionally we have like ABCD range, right? So what we can do is from B we can always go to right up till we reach in the range C to D, right? And if this exceeds, it jumps more than D, then I know that it's not possible ever to get on C, right? Because B is the last element which I can start. So if there is any element less than B over here, it's not working. Yeah, API problems are hard. That's why you should do subtasks. Yeah, so you know that if there's any position over here which is less than B, then it will go through B before going through this node, right? And if there's node greater than B over here, then still it will go through some of the nodes over here, right? Because B is less. So the if it's like going past, then its answer is not possible. Else if it's going somewhere, let me say that this is going over here. Now for from B, I can go some max. Let's assume that we start only from B. Okay, so from B I can go to some max, and from here I can have might have jump over here, right? So suppose this is the max, then it's like not going over here. Going over here is a waste because it will again come over here, right? So here we use the max tree to go over here, but suppose the max tree points over here, so we know that this is less than this max, right? So now this max should point either to this or greater, right? So distance of this is either the same when we go right or we go through max, or for this and for this all it becomes less because it's just 1 and 1 2, right? And conventionally it's going more. right? So the best possible method to least jumps will always be from going through max, right? Because you reach faster than when we go through maxes, right? But after some point, you might be like paring this part. So those max we don't need to take. And why am I starting from B and taking maxes is because I don't know which maxes should I take over here. But here, this is the conventional way to jumping, simple method. And here from going to maxes, I'm saving some of the steps, right? So that's why using max over here, max over here, max over here, so that I save some steps. And if it's still in A, then it's like the first move. So I don't calculate this steps. If it's greater than A, it's like going left to the A, then I calculate that step. That's another casework which might forget. So that is another casework. Right. So you just need to go max over here and come over here. And you need to go right, and for when CD is on the left, you need to go left and find max, will find max, right? So your answer would be, what would be your answer? So you need to find a position over here or over here, like the start, and you need to keep taking max until this is less than start, because then you can come to the start. Like this is height, and this should be less height, only then you can reach, right? But you keep taking max because max gives you always the best minimum number of steps to reach, right? So that's why you should use max. And but you can't use, or suppose now there's a possibility that this max is like exceeding this, right? There was some possibility. So basically you need to have two maxes. First max is when, yeah, so first max is when this goes to this point, and the second max is when this goes beyond that point. Okay, that we will go across when we go to the code. So basically this is the thing. So let me go. It's like, as we go on through the code, if anything is still remaining to explain, I'll just keep explaining. This is graph L, graph right, and max graph. This is left edge for each, right edge for each array, and this is binary lifting for each. Yeah, so basically for each minimum steps, you can do binary lifting. So this is init function. So you use stack, and you use nth position, which is the maximum height. So all the positions will, this is the root node basically, so that we can easily have a DFS. So this is just popping and a standard method of finding the left edge. I think you should be knowing this method. If you, it's a very common method. If you don't, then you can just understand or have some. There was some problem, such problem on this. I don't remember. It was a code chef problem. It was like a long problem. 10 days contest ka problem. But never mind. That I was unable to do it when I was like, I was not so good at that time. That included math and this type of stuff. Never mind. And similarly I do for right edge, and this is left edge to I and right edge to I to right edge again I store in an array, and this I store in a graph, because I will be looping like root. This is like I will be using the directed edges, will be I'll be using these directed edges, but for traversing I have an end, and I will be using this edges, right, to traverse down, because it's a binary lifting this side. So like I have an, like I have inwards, right? And this is like casework of going to N and finding the best maximum height one. DFS L, DFS R is the L graph, R graph, and the max graph you can't start from N, because in binary lifting you never want to go to N. It's because N is again out of bounds, so you will find the maximum position, and you know that maximum position also everyone will be visiting the maximum position. You can just binary search for maximum position. Maximum position will be the root, but not necessarily in left and right, because left and suppose maximum position is on the right, then you only go on left, so you never reach the maximum position. Hence, you need to find some node n common node for everyone. And this is the request for maximum position. DFS is just going binary lifting, basically normal graph you have, and which is binary lifting. Now answering the queries, it's like this is the base case that if both the queries, both the ranges are intersecting, then the answer is 0. And if it's like a type left and type left, type right is what I'm going to explain, like AB to CD, right? So if A is greater than B, then it's inverse. Like I will be going to type right now. So in type right, you go binary lifting, comma 0. So basically, binary lifting R, where is the function? Yeah, so basically you just start, and till time it's like stop is nothing but the C, and you start at B and you stop at C, right? So you know that it's not end and it's greater than stop. Oh, that's for L, right? Binary lifting R. It should be less than C, right? So it's less than C and it's not N. You keep going up and just return the start. You're not returning plus one value because we are using this twice function. So that's the reason. But you do plus one value over here. So you do plus one value over here. Like the next, so you find the first element in the range C to D. If it's not in the range C to D, then answer is -1. But if it's in the range C to D, then the max position is the maximum position that you go. So basically, thing is from A, B, C, D, you have a maximum position over here from which you go in the directly go in this range, right? So it's always optimal to go like to less than this maximum position, go to the maximum position and find the best place, or you go above this maximum position, and like if by going to max you reach the maximum position, then that's only one option. But else, if there is a way to going above the maximum possible equation, then you again need like to come over here, right? So and this is also like 1 2 steps, and this is also 1 2 steps, so you check both the things because this might go out, right? That's the thing. So this is the maximum position which like you should go on. So that's why take the maximum position and don't do comma 0 because we don't need the position in C comma D. So this is like before C, we find the maximum position, and area of max pos will be with the value of that maximum position, and BLRBA pos. So basically this is just removing while we go maximum. If it's in the range B to A, then we don't actually include that, right? So still it's the range B to A. So BLR is like this is less than max because you don't want to exceed area of pos, right? And it's greater than equal to n. While you go left, start is here. Basically, you're just going left. Where was I? Yeah. So basically, this is left graph only. This is not max graph, right? So you're just going left and finding the maximum position which is less than max and return that position. And once you return that position from arrow position, and you will like go from A to B. So this is like final BLR. So this is going max. Now you go max while it's less than stop. Stop is like the max position you have. And after that, if answer arrow start, so stop, then you return answer which is 0, because when you start it's the same as when you stop. The answer is 0. So basically it's like from here you go to a node over here, right? So if you have reached over here, like start is stop. So what is stop? Stop is nothing but array of pause, which is the maximum array you get. Pause is the range in C to D, right? So it's like going more and going over here more than pause once, or going less than pause. So basically the two cases are A, B, C, D. This is the pause, which is the first element you visit. Now either you go less than pause, go some node here, go some node here, visit this, or you go more than pause and you go some node. Right? These are the two possible cases that you can have. So like after this position, you only go right. You don't go max because max is more than pause. So from this, you only go right or you go max and then you like over jump that, right? So if stop is nothing but the start, then you know that you already are already in those range. Else we have the start and we just go right. So this is like going maximum up, right? And max if this is, and you get answer. And if it's not, if now we only go right and we have that as one answer. The second one is we go one more step to the max, we don't go to the right, and then we just take that if it's like a valid node, then we go up and we go right. So there are two things, right? And then we, if it's less than mx as well, so max in range C to D, if it's less than that, then answer is with both res and res1, else only the first condition is satisfied, and then we just print the answer. That's it. I hope you got it. Well, do you have any doubts? Then let me know. This was for the day. Thanks for attending the lecture. I hope you liked it. You all guys can leave. Thanks. Yeah.